In this video, we're going to have a look at part B of work done by a force using vectors. We're going to have a look at a situation first where we've got an inclination of an object that's not on a horizontal distance. So again, we're going to be using the scalar projection of a force along its direction times by s, the meters in distance that it's going to travel. And in our last example, we're going to have a look at a moving body over a displacement d and work out the work done in joules in these situations. So in situation 3, we have a body of weight 100 newtons is rolling down a plane. So this is where we've got that we're not on the ground. It's rolling down a plane, inclined at an angle of 45 degrees with the horizontal. The body experiences a reaction force, and we're going to call it T, newtons. This is perpendicular to the inclined plane, and what we've got therefore is this reaction force heading up in this direction, and we've got the ball rolling down as a result. But we have a 20 Newton opposing force, opposing the motion of that object. So what we first want to do is find the magnitude or the size of T, our reaction force. So if we consider that we've got a 45-degree inclination, we've got this force travelling up in its direction, and obviously it's counteracting that 100 Newton weight of the body. We can just rearrange to see a nice right-angled triangle here. So in this right-angled triangle, from the 45, we can work out the size of that reaction force T. Looking from the angle, we can use the opposite over the hypotenuse. So the sine of 45 degrees will be the size of that force over 100. So the magnitude of force T is going to be 100 times the sine of 45. And we know the sine of 45 is root 2 on 2, so its size is 50 root 2 newtons. Next, we'd like to find the magnitude of the resulting force in the direction of the motion of the body. So this is basically talking about what's the resulting force. Now we know the result is that ball is rolling down that hill. So we've got the projection of the force T on the direction of the ball, and we also have to take away that opposing force, that 20 newtons. So what we want to find from our first right-angled triangle previously is this value that is going to be the result of the projected reaction force T. So if we use that same right-angled triangle above, we can work out, looking from the angle, that we want to find this side, projection of the force T, which is the adjacent side over the hypotenuse of 100. So we could say that this is represented, just get rid of that. The cos of 45 is going to be the projection of T onto the direction that we're trying to travel over 100. So the projection of that force is going to be worth 100 times the cos of 45. And we know that cos of 45 is also root 2 on 2, so the projection is 50 root 2. So we can equate this to 50 root 2 take 20, and that is going to be equal in newtons to the size of the result that we have. The result of that force T against the weight of the object of 100 newtons and opposing that 20 newtons that's pulling it in the other direction. So what we want to do now is work out what is the actual force done what is the actual work done by the force, the resulting force. And we can see here that if we want it to move 1.5 meters along that inclined plane, so rolling along, the work done from our previous Part A video, we can see is the size of the result times the 1.5 meters we want to move. So it's going to be 50 root 2, take 20 lots of 1.5. We can actually work out the decimal here is 76.1 joules. So let's take a look at a different type of question. We want to know what work is done when the ball has reached a descended distance of 1 meter below it where it was before. So if we go back to our picture of the object on that inclined plane, we want to know when it has rolled enough to be in line with 1 meter below where it currently was. So we actually need to know this distance here first so we can work out the work done. Again, because we're taken from the original picture, we're just trying to work out when it's in line with 1 meter drop. So we've got at 45 degrees. So looking from that angle, we need to find how far along that incline it's rolled down. So we can call that our distance d. So the sine of 45 degrees is going to be 1 over the distance. So the distance is going to be 1 over the sine 45. Sine 45 meaning 1 over root 2 on 2, which gives us root 2 meters. So therefore, the work done now by that force is going to be the size of that result, which we know, which is 50 root 2 take 20, times by a distance of root 2 that it is going to be rolling down. And that will give us 71.7 joules. So very similar to our previous video, but we've just got it on an inclined plane rather than on the ground, that horizontal distance. In situation 4, we're going to consider that situation where we're going to have a look at the displacement. And that was where we said that the work done was going to be equivalent to the force times by the displacement, and that will give us a result in joules. We've called that displacement here D. So what we want to do first is find the scalar projection of the force onto the displacement vector. So what we've got is we've got a body that's moving 5i plus 3j, or 3 meters. And it moves in that way when it has the resulting, that the force of 1 newtons applied to it. So here is our displacement, if you like, D, when we've had the force of 1 applied to it. So we want to know the projection of that force is going to be equal to the scalar product of the force with the unit vector of the displacement, because that's the whole displacement including how far it has moved. So if we have a look at the displacement 5,3, the unit vector for this is going to be 1 over the magnitude of 5,3, which is going to be the square root of 34. And that's going to be scalar product with the force vector 1. So we end up with 10 on root 34 plus 3 on root 34, which gives us 13 on root 34. And if we rationalise it, it will be 13 root 34 on 34 newtons. So this is the size of that projection of the force onto its movement of that body. So that's just the size of how it has forced it to move. But we want to find now the vector projection. So let's call it the vector V. To find the vector projection of that force, Well, it's going to be the size of that force. So 13 root 34 and 34, that's the size, times by the actual unit vector to get the direction, because we've got the size, now we need the direction. And that is going to be the unit vector of the direction we're travelling in. So when we simplify this, we end up with 13 on 34 in the direction of 5.3 newtons. So we've got its size, and now we have got the size and direction as a vector. So now we can use that idea of the work done is the force times the displacement. So the work done is going to be the force multiplied by the displacement. So we can do this in two ways, just by using the scalar product. We get 10 plus 3, which is 13 joules. But another way we can work out the work done is to also go back to our other explanation or calculation, which was the scalar projection of the force times by the distance it's moved, which was s. Now we know we've got the size or the scalar projection of the force, which was 13 root 34 on 3, that 34, that was its size, and its movement in meters is going to be the magnitude of its movement, its displacement. And we know that that is the square root of 34, so we can multiply that there. And when we do that, we again find that we have a solution of 13 joules. So in summarising, there are two ways that we can calculate the work in joules that is produced by a force on a body, whether it's on the horizontal ground, whether it's inclined on a plane, and whether it has any opposing forces to it as well. And even if we're given its displacement. If we've got its displacement, we can find out the unit vector, and we can also find out the size or the magnitude of that movement or that displacement.